Hello everyone, I am Bireshwar Roy. I am currently pursuing my fourth year PhD in the Department of Physics, Indian Institute of Science, Bangalore. In this NPTEL GATE Physics course, I will be discussing some previous year's GATE Physics questions and try to solve them with proper explanations. This question was asked in the GATE Physics paper 2020. This is a numerical answer type question having 1 mark. The topic of the question is electromagnetic theory. The question is, a conducting sphere of radius 1 meter is placed in air. The maximum number of electrons that can be put on the sphere to avoid electrical breakdown is about 7 times 10 to the power n, where n is an integer. The value of n is, so basically we have to find the value of integer n. In this question, we have to assume breakdown electric field strength in air is mod of E vector equals to 3 times 10 to the power 6 volt per meter. Permittivity of free space is epsilon naught equals to 8.85 times 10 to the power minus 12 farad per meter. And electronic charge E equals to 1.6 times 10 to the power minus 19 coulomb. Let us see how to solve this problem. It is given in the question that a conducting sphere of radius R equals to 1 meter is placed in air. The breakdown electric field in air is mod of E vector equals to 3 times 10 to the power 6 volt per meter. The permittivity in the vacuum epsilon naught is 8.85 10 to the power minus 12 farad per meter, and the electronic charge is 1.6 times 10 to the power minus 19 coulomb. Now we know the electric field on the surface of a conductor is given by E equals to sigma by epsilon naught, where sigma equals to charge density on the conductor surface. Now if n is the number of electrons on the surface of conductor, then sigma is given by n times E divided by 4 pi r square. So this is the surface area of the conducting sphere. Hence, the electric field on the surface is Ne divided by 4 pi r square times epsilon naught. To avoid the breakdown, the maximum number of electrons that can be put on the sphere is n equals to 7 into 10 to the power n. Here we have to find the n, and the corresponding breakdown electric field mod of E that is given in the question is 3 times 10 to the power 6 volt per meter. So we will put all the values in this equation. So our maximum value of E is 3 times 10 to the power 6, that is equal to n times E, so 7 into 10 to the power n times 1.6 times 10 to the power minus 19 divided by 4 pi r square epsilon naught. So 4 pi times 1 square, because r equals to 1, the radius equals to 1, times the permittivity in vacuum, that is 8.85 times 10 to the power minus 12. So we have 10 to the power n equals to 3 times 10 to the power 6 times 4 pi times 1 square times 8.85 times 10 to the power minus 12 divided by 7 times 1.6 times 10 to the power minus 19. If we calculate this, we will get approximately 10 to the power n equals to 3 times 10 to the power 14. So n equals to log of 3 times 10 to the power 14. This will give approximately 14.47. So the value of n in the integer form is 14. Although the value must lie in between 14 to 15. If you get the answer 14 or 15, that is also correct. So according to our solution, the maximum number of electrons that can be put on the sphere to avoid electrical breakdown is about 7 times 10 to the power 14. So the n value is here 14. This question is from the GATE Physics paper 2020. This is a numerical answer type question having 2 marks, and the topic of the question is quantum mechanics. The question is, the radial wave function of a particle in a central potential is given by r as a function of small r, that is position, equals to a times small r by a times exponential of minus small r divided by 2a, where a is the normalization constant and small a is positive constant of suitable dimensions. If gamma a is the most probable distance of the particle from the force center, the value of gamma is, so we have to find the value of gamma so that the gamma a is the most probable distance of the particle from the force center in this question. Let us see how to solve this problem. According to the question, the radial wave function is given by r as a function of position small r equals to a times r divided by a times exponential of minus r by 2a. Therefore, the probability of finding the particle between r and r plus dr is given by p as a function of r times dr equals to 4 pi r square times mod of capital R as a function of smaller mod square equals to 4 pi a square divided by a square times r to the power 4 times exponential of minus r by a times dr. Here a is the normalization constant and a is the positive constant of suitable dimensions. To find the most probable distance r of the particle from the force center, or the value of r where the probability of finding the particle is maximum, we can say in this case the derivative of the probability density function Pr with respect to the position r should be 0. So this will give ddr of 4 pi a square divided by small square times r to the power 4 times exponential of r minus r by a equals to 0. So if we do the derivatives, so we'll get 4r cube times exponential of minus r by a plus r to the power 4 times minus 1 by a times exponential of minus r by a, that is equal to 0. So we can do the little rearrangement here. So we'll get 4 minus r by a times r cube times exponential of minus r by a equals to 0. Therefore, we can say 4 minus r by a equals to 0, since the other terms with it, that is r cube times exponential minus r by a, that cannot be 0 here. So from here we will get r equals to 4a, given the most probable distance is gamma a. So if we compare this with 4a, then we will get gamma value is 4. So if gamma a is the most probable distance of the particle from the force center, then the value of gamma will be 4. Now we will discuss some important tricks to solve this kind of problem. So the radial function given in the question is similar to the radial part of the hydrogen atom wave function. For the hydrogen atom problem, if the radial part of the hydrogen atom is proportional to exponential of minus r divided by Na, therefore the principal quantum number in that case will be n. And for the principal quantum number n, the probability of finding the particle or electron in the hydrogen atom problem is maximum at r equals to n square a. So if we use this relation, so in the given question, it is the n value is 2. So the most probable distance will be r equals to 2 square a, that is 4a. So our gamma value will be 4 in that case. So we have solved this problem, and also we have discussed some important tricks to solve this type of problem very easily. And we found that the gamma value in this question is 4. This question was asked in the GATE Physics paper 2020. This is a numerical answer type question having 2 marks, and this question was asked from the topic quantum mechanics. The question is, a free particle of mass capital M is located in a 3-dimensional cubic potential well with impenetrable walls. The degeneracy of the fifth excited state of the particle is, so we have to find the degeneracy of the fifth excited state of this particle in this cubic potential well. Let us see how to solve this problem. We know the energy spectrum of the 3-dimensional cubic potential well of site capital L is E nx ny nz equals to pi square h cut square divided by 2 capital M capital L square times nx square plus ny square plus nz square. Here h cut is the reduced Planck constant. Capital M is the mass of the particle in this 3-dimensional cubic potential well, and L is the side of the well, and Nx, Ny and Nz denote the 3 quantum numbers for this problem. So we can write this as alpha times P, where P is this sum, that is Nx square plus Ny square plus Nz square, and alpha is this constant term, that is pi square h cut square divided by 2m capital L square. Here nx, ny and nz, all of these quantum numbers can take the integer values, that is 1, 2, 3, 4 and so on. Let us see the energy configuration for a free particle in 3-dimensional cubic potential well with impenetrable walls. We'll see it in the next slide. Now, let us see the possible energy configurations for the quantum numbers nx, ny, nz and their corresponding energies and degeneracy. So, for the ground state, nx, ny and nz, all of them will be 1. So, for the set 1, 1, 1, the p value is 3. Here p is the nx square plus ny square plus nz square. And the corresponding energy value in the ground state is E1 equals to 3 alpha. So here only one possible set is there in the ground state, so degeneracy will be 1. In the first excited state or the second state, the nx can take value 2, ny can take value 1 and nz can take value 1. Or alternatively, the other possible sets are 1, 2, 1 and 1, 1, 2. So there are 3 possible sets in the first excited state. The p value will be 6 for all of the states, and the energy value E2 will be 6 alpha. And clearly their degeneracy is 3 in the first excited state. Similarly, for the second excited state, the possible sets for the nx, ny, nz are 2, 2, 1, 2, 1, 2 and 1, 2, 2. The p value will be 9 here, and the energy value for this second excited state E3 is 9 alpha. So the degeneracy here is 3. For the third excited state, the possible sets for the quantum numbers nx, ny and nz are 1, 1, 3, 131 and 311. So 3 possible sets are there. The p-value is 11 and the energy value for this third excited state E4 equals to 11 alpha, and clearly the degeneracy is 3 in this third excited state. For the fourth excited state, only one possible set is there, that is 222. The p-value is 12 here, and the energy value for the fourth excited state E5 equals to 12 alpha. So the degeneracy is 1 in this state. And the fifth excited state will have the possible quantum number sets, that is 123, 213, 231, 132, 312 and 321. So all the 6 states will lie in the fifth excited state, and the p-value is 14. The corresponding energy value for this fifth excited state is E6 equals to 14 alpha. So the degeneracy in the fifth excited state is 6. The fifth excited state of the particle has the energy E6 equals to 14 alpha, that is actually 14 times pi squared h car squared divided by 2m L square. The possible sets of quantum numbers that we have seen in the previous slide, nx, ny, nz, are 123, 213, 231, 132, 312 and 321. So there are 6 possible sets. So the degeneracy of the fifth excited state of the particle is 6 here. We have discussed the solution for this question very thoroughly, and we found that the degeneracy of the fifth excited state of the particle in this cubic potential well is 6.